Hi, my name is Matt Duff, and today we're going to talk about digital versus analog filters and the advantages of each. So let's jump into the advantages of a digital filter. So the first advantage of a digital filter is that it's programmable. So digital filter has a set of coefficients, it has a clock rate. Typically both of these are pretty easy to change. So if you have an application that needs different filtering requirements that you need to change on the fly, a digital filter is a really good way to go. Another big advantage of a digital filter is that it's repeatable. So the product you ship today and the product you ship a year from now are going to have the exact same performance. The product that you have at 25 degrees, when you put it at 85 degrees or you put it at minus 40, it's going to have the exact same performance. So that's another nice advantage of a digital filter. And then the final advantage of a digital filter, if you're using an FIR, so this doesn't apply to IIR, but if you're using an FIR filter, that inherent in the architecture is that you're going to get this constant time delay. So if you're filtering something that you want to look at in the time domain, then you know that you're not going to get any distortion from one frequency arriving earlier than another frequency. Now, with analog filters, you can build a Bessel filter, and the Bessel filter is going to get pretty close to that. It has a constant time delay, at least in the passband, but it's not, with analog filters, it's not inherent in the architecture like it's inherent with an FIR filter. So those are some advantages of digital filters. What are advantages of analog filters? So the first big advantage of analog filters is that you don't have to worry about aliasing. So with a digital filter, it's only really as good as the ADC. So if a frequency gets through the ADC that's beyond the Nyquist of the ADC, the filter isn't going to be able to differentiate between that and the lower frequencies. So you may not reject it like you might want to. Another advantage of using an analog filter is that obviously you don't have to do all the work in the digital domain. So let's say you've got a microprocessor that you really like, you've written code for it, and now you have a new requirement that requires filtering. And maybe those calculations to do that filtering is too much for the microprocessor that you have. So you could go to a fancier microprocessor, you could add an FPGA that then communicates with the microprocessor, but often it's a lot easier and less work if you just add some components in front of the ADC to do that filtering in the analog domain. It's all nice and self-contained, and you don't have to worry about new coding and so forth. And then finally, which I think is probably the biggest advantage of using an analog filter, is that it lowers the ADC requirements. So if you think about it, what a filter does is it removes data. So you've got the good data that you want, and then you've got the bad data that you want to get rid of. Well, if you wait until after the ADC, then to do that, which is what you have to do in a digital filter, then the ADC has to both digitize the good stuff that you want and the bad stuff that you don't care about. But if you do that filtering before the ADC, then you can get rid of that bad stuff. And that means that either, depending on the type of filtering that you're doing, either that means that you can use a lower sampling rate on your ADC, or that your ADC doesn't have to have as large a dynamic range. So that means you can either get a cheaper ADC, or if you're pushing the boundaries a lot, it may be that there's not an ADC out there that does what you need if you try to do it in the digital domain. But you might be able to accomplish it if you did the filtering in the analog domain. So those are some pros and cons of analog versus digital filters.